Well, in case you didn't get enough of optimization last night, we've got ourselves another treat and we're going to practice a little more tonight. Now, these tend to be just a little trickier, so take your time and pause, rewind when you need to. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So again, here's, why this is important. Have you ever got like a box in the mail and, you ordered something fairly small and it comes in this gigantic box? Such a waste of money. So here's where an engineer would get paid, quite a bit of money to maximize or minimize the volume of the box. So anyways, back to our problem. It does say we have a square base. All right, so keep in mind that this bottom should be a square, therefore its dimensions are going to be x by x, all right, because it's square. The other key idea was that we have an open box, okay? There's only 5 sides that means. There's the 4 surrounding sides and the bottom, but the top is going to be open. And what else do we know? We have obviously some height, we'll just call h for now. So my primary equation, remember, is the one that we want to minimize or maximize. And it says I want to maximize the volume. Well, the volume of a box is length times width times height. So in this case, my volume is going to be x by h, or x squared h. Now, if my volume was in terms of one function, I'd be done and I could take the derivative and solve my problem. However, it's not. So I need to slow down and think about what my secondary might be. Now, your secondary equation is the one that has the fixed amount. And they told us we had to have 108 square inches of surface area. All right, so let's write our secondary equation about surface area. I would say 108 is equal to the sum of all the surfaces. Well, the bottom surface is x squared, and remember, there is only one of those. And then I have the 4 equal sides, which are x by h, so I'm going to say 4xh. Now, my goal is to put my primary in terms of one function. So I would say to myself, it's probably easier to solve this equation for h than it is for x. So I'm going to quickly solve that for h and say that's 108 minus x squared divided by 4x. And I'm going to substitute that h into my primary equation. So volume equals x squared times 108 minus x squared all over 4x. Now before I do any calculus similar to related rates, clean this puppy up. It makes no sense to make your math harder. I'm going to cancel this x with one of those, okay? And I'm going to really bring that out as a fourth. So I'm going to distribute a 1/4 x. So 1/4 x times 108 makes 27x minus 1/4 x cubed. Do you see how much nicer that function is to take the derivative of than this mess? All right, so slow down and apply some steps. It will make your life easier. Now I'll take my derivative. So I've got 27 minus 3/4 x squared equals 0. So I've got 27 equals 3/4 x squared. So that's 108 equals 3x squared. 36 equals x squared, therefore x equals plus or minus 6. Now let's use some common sense here and talk about what the domain could be. Since we're talking about x and y values, clearly you don't want a negative value to make this side of your box, so I know my domain has to be greater than 0. So I can right away reject that -6 and just use my +6. And I'm going to find my nicest version, which I think is this one, and plug in a 1 and plug in a 7. If I plug in a 1, I clearly get a positive. If I plug in a 7, I get a very negative. So I have proven that I have maximized this box when x equals 6. Now, let's just make sure we've answered that question. Question does say, what are the dimensions that will produce a maximum box? So I had 108 equals x squared plus 4xh. And I can easily solve for h there, so I have 108 equals 36 plus 24h. and I get a nice h equals 3. So my dimensions are 3 by 6. All right, if a cylindrical tin can with an open top is designed to hold 30 cubic centimeters, what circumference will maximize the amount of tin needed? Now I'm going to warn you, the cylinder is usually the nastiest one. So pause it when you need to, slow down, replay it, so you get what we're talking about here. So let's just start with the shape. We can all picture a cylinder or a tin can. Now the deal is they said it has an open top, so basically there's nothing here. All right, so you opened up your can of chicken noodle soup, and you have this nice base, and you have the cylinder here. The question says you want to maximize the amount of tin. Well, if you're talking about the amount of tin used to create this, I want to be clear that the question is trying to maximize the amount of surface area. So my primary equation is the one I want to maximize or minimize, so I want to get this guy's surface area. Now surface area, again, is just the area of every surface. So let's start with our bottom surface. That's the easiest. That's a circle, so that's my pi r squared. And now comes the tricky part. I need to get the surface area of the shape that's around the outside of the cylinder. Now we all took geometry, so hopefully you can picture this. Basically, if I were to picture it as a soup label, and if I were to cut the soup label off and open it up, I think you would agree that you really just have a rectangle that's been twisted so it turns into a cylinder. So I really just need the area of this rectangle. Now the height, I'm just going to label it as h. But here's the tricky part. Here's what you have to keep in mind. This distance at the bottom goes around the base of the circle. Okay, when you put those two ends together, you create this circle. So this distance on the bottom is actually the circumference of the circle. All right, so if you need to slow down and replay that, go ahead. But that distance is actually the circumference of the circle. And my circumference is 2 pi r. So the area of the soup label, so to speak, the outside of this tin can, I'm going to add is base times height, so 2 pi r h. So this represents my primary equation. Now it would be really nice if I was in terms of one variable, but I'm not. I have this stinking h at the end, so that means I have to have a secondary equation. So let's slow down and go get our secondary equation. They told us that we have a fixed volume of 30 cubic centimeters. Now, I know they didn't use the word volume, but the word cubic centimeter should have given that away. So I'm going to say my volume is 30, and the volume, of course, is the bottom shape, pi r squared, and if I fill it up, I multiply by the height. Okay. Now, I don't have any numbers to plug in, so really, I'm just solving for h. h is equal to 30 over pi r squared. And that's what I need to substitute into my primary equation. So I've got surface area equals pi r squared plus 2 pi r, and in place of h, I'm putting 30 over pi r squared. Now, we've talked about cleaning these up. I certainly wouldn't take the derivative until this is cleaned up. So I've got surface area equals pi r squared plus, let's see, the 2 and the 30 make a 60. This pi will cancel with this pi, and I have r over r squared, so I'm going to bring that up as r to the negative first. Hopefully you realize that is over 1r. All right, now because I want to maximize or minimize, in this case I think we were minimizing, all that means is at that lowest point I have a slope of 0. So I am setting the derivative equal to 0. So I get the derivative of surface area is 2 pi r plus, I guess I could say minus 60 over r squared. And I'm setting that equal to 0. Okay, now, just like we've talked about over and over, we're not going to kill anything, we're going to get one common denominator. So I'm going to multiply this top and bottom by r squared, so I have one big fraction. So I get 2 pi r cubed minus 60 all over r squared equals 0. Now I'll set both the numerator and the denominator. This is the easy part. So if I set the denominator, I clearly get r equals 0. If I set the numerator, minus 60 equals 0, I get, let's see, pi r cubed equals, I'm going to add the 60 and divide by 2. It gets me a 30. I get r cubed equals 30. So over pi. So r equals the cubed root of 30 over pi. Now, perhaps not the nicest looking number, but it's actually not that bad because keep in mind, pi is really 3.14, 30 divided by 3.14 is a little less than 10, and you're taking the cubed root of that. Anyways, we got 2 critical points, and let's think about our domain. Since we're talking about a radius of a soup can, clearly, we can't have a radius of 0 or a negative, so I know 0 is going to be my min, and I'm going to say this is my surface area derivative. And I have a cubed root of 30 pi. I'm going to find my nicest version, and that, of course, is my fraction here to plug, oh my goodness, my pen, plug these into here. If I plug in a 1, I get 2 times pi times 1, and remember pi is 3.14, so I get 2 times 3.14, so a little bigger than 6 minus 60 is clearly a negative over a positive. It gets to be a negative. And I'm going to plug in like a 5 here. 5 cubed is 125 times 2 is clearly bigger than 60. I get a nice minimum value. Now, don't forget, we actually should answer the question. The question says now, what circumference will maximize the amount of tin needed? The question actually wants to know, what is the circumference that we need? Well, remember, circumference is 2 pi r. And we just figured out we will have a minimum circumference when the radius is the cubed root of 30 over pi. And not the prettiest, but that's our final answer there. Our next example is about a Norman window that is constructed by adjoining a semicircle to the top of an ordinary rectangular window. So I'm just going to slow down and sketch out what I have. I have this nice rectangle, okay, with opposite sides congruent, and I'm attaching a semicircle on top of it. Maybe you can picture a window like that. Maybe you have one in your house that looks like that. Find the dimensions of the Norman window of a maximum area. Okay, so there's my primary. I want to maximize the area, whose perimeter is 16. So there's my secondary, my fixed amount. All right, so let me start with that primary. It's got to be about area. And now let's go ahead and assign some variables to this function. So I'm going to say this is y by y. Okay, now watch how creative I get. Basically, this represents the what of the semicircle. I'm going to call that my radius. Therefore, on this side, I'm going to say this distance is actually 2r. And that's kind of the whole key to the problem. If you catch that piece, you're usually in good shape. So again, I'm going to use this as my radius, r. Therefore, this side is made up of 2 of them. I'm going to say this side is actually 2r. All right. Now, we want to maximize the area. So let's go ahead and write the area function. The area of this rectangle is just length times width. So I'm going to say that's 2 times r times y, plus I need the area of a semicircle. Now notice I'm using the word semi. That means it's half a circle. So that's 1/2 pi r squared. All right, so you'll notice I have r's and y's. So that means I need to use my secondary. So let's go get our secondary equation. We have a fixed amount of a perimeter of 16. Okay, now what does the word perimeter mean? Perimeter tells us to add all of the sides. Now, just take your time with this one. I'm going to have y plus 2r plus y. Would you agree that's the perimeter, the outside edge of this? So let me say that again. That's 2y plus 2r. Now here's where it gets tricky. All right, so I've covered this outside edge, this outside edge. How do you describe the outside edge of a circle? Okay, what is that called? Think back to your geometry days. That's called your circumference. Okay, now the circumference formula, we know this from our related rates, is 2 pi r. But you only have how much of the circumference of the circle? Half. So I can basically multiply by half or kill the 2. So I have to add on pi r. Now, since my primary had an r and a y, I need to solve this equation, and because there's only one y, it's easier to solve for y. So I'm going to say I have 16 minus 2r minus pi r equals 2y. And then I'm going to go ahead and divide every term by 2. So I get, let's see, that's 8 minus r minus 1, or I guess I could say half pi over 2r equals y. And I need to take this and carefully substitute it into y. So I've got my area equals 2r times 8 minus r minus pi over 2r plus 1/2 pi r squared. All right, now before I take that derivative, I'm going to clean it up one more step and I'm going to multiply these together. So I have area equals 16r minus 2r squared minus pi r squared plus 1/2 pi r squared. Okay, when I did this 2 and that half, that canceled there. Now I can take my derivative and set it equal to 0. So that becomes just 16 minus 4r minus 2 pi r plus half times 2 is gone, pi r equals 0. I'm going to keep cleaning it up. You'll notice I have two like terms I can actually add together. So I get 16 minus 4r minus pi r equals 0. And my goal is to solve for r. So I've got minus 4r minus pi r equals negative 16. And I'm going to factor out the r by saying that's negative 4 minus pi. And r equals, let's see, negative 16 all over negative 4 minus pi. Now if all those negatives freak you out, remember as long as you change every sign, you're in good shape. So I'm going to say that's 16 over 4 plus pi. And that is the length of my radius. Again, not pretty, but that's my radius. Alright, so let me just make sure I answer the question. I want to maximize the area. So I just want to prove that I actually have a max and find the dimensions. Alright, so again, I wouldn't want any negatives. So that was my A prime, that's my A. Let's see, I have 16 over 4 plus pi. Now don't let that freak you out. Remember, pi is like 3.14. So I basically have 16 divided by 7.14. Well, 7 goes into 16 how many times? Twice and a little more. So I could test a 1 here, and I could test a 3 here. If I plug in a 1, now again, I'm going to plug it into some place where I have my derivative equal to 0. Alright, and that's where my derivative equals 0. That would be 16 minus 4 minus 3.14 is clearly a positive. And if I plug in a 3, that would be 16 minus 12 minus 9 something, which is clearly a negative. So you can see I am maximizing when my radius equals 16 over 4 plus pi. Now again, it wants the dimensions, so I would just carefully take that value, plug them back into my original someplace to figure out what my dimensions are. Alright, I've got one more for you. A closed rectangular container with a square base is to have a volume of 300 inches cubed. The material from the top and bottom of the container will cost $2 per inches squared, and the material for the sides will cost $6 per inches squared. Find the dimensions of the container that will give us the least cost. So basically, that's what I want to minimize. If I want the least cost, I'm saying to myself, I want to minimize the amount this is going to cost. So my primary equation, remember, is the one I want to maximize or minimize. So I want to write this one about cost. Alright, so it's very similar to the other ones. We're just going to have some, dollar values involved as well. Now, if I have a square base, alright, that's going to get me x by x, which is x squared, and I hope you'll agree we'll have 2 of those. So I'm going to say that's 2x squared. Now I have to multiply that by how much it costs to create that side. And it says material for the top and bottom will cost $2, so I'm going to multiply that by my $2. Plus, these sides that I'll put in blue here are x by h. And how many of them do we have? I would say we have 4 of them. And that's going to cost me $6 per side. So this is the function I want to minimize. Okay? This would be the area of the side times how much it costs, the area of those 4 sides times how much it cost. And of course, surface area we're talking. Now, I obviously have to have a secondary because I have x's and h's. And my secondary is that fixed amount. And they're telling me you have to have a volume of 300. So I know the volume of this is 300. Now remember, your volume is your length times width times height. So I can say that's x by h equals 300, or x squared h equals 300. And I want to clearly solve for h, so I get 300 over x squared. And that, my friends, is what I will substitute into this function. So I'm going to say my cost is, let's see, that's 4x squared plus 6 times 4 is 24. I have an x, and in place of h, I'm putting that 300 over x squared. Okay, now again, before I do any calculus, I'm cleaning this up. So I've got 4x squared. 24 times 3 gets me, what is that, 72. And I'll add my 100, my 7200. And this is x over x squared, which is over x, and I'm going to bring that up as x to the negative 1. Now that I've cleaned that function up, I can take a quick derivative, and you'll see how simple this is. I'm going to minimize or maximize my cost here. See, that's 8x minus 7200 over x squared. Set that equal to 0. Grab myself a nice common denominator. So I'm going to multiply this fraction by x squared. So that gets me 8x cubed minus 7200 over x squared. Okay, so now I'm going to set, of course, that top and bottom equal to 0. So the bottom is just x equals 0. And my top, I get 8x cubed, whoops, my pen is dying here, equals 7200. Let's see, that's x cubed, 8 goes into 72 9 times, that's 900. So I get x equals the cubed root of 900. Now, I clearly have two critical points, 0 and the cubed root of 900. I'll put those on my chart, and I'll just look back. I wanted the least cost, so I want to minimize the cost. Clearly, I'm not going to have a negative x value. I know my domain starts at x, so I've got the cubed root of 900. Okay, that's c prime, describing the cost. I'm going to safely plug in a 1 there. And if I plug in a 1, I'm going to use this nice fraction. On the top, I get 8 minus 7200, which is a negative, over a positive gets me a negative. I don't know the cubed root of 900, but I know that, just this is how I think of it in my head. I know 10 cubed is 1000. So the cubed root of 1000 is 10. Therefore, if I want the cubed root of 900, I know it's less than 10. So I could pick 10 would be a very safe number to pick here, or even 11 if you're worried. And clearly I'll get a positive value there. So I have created a minimum when x equals the cubed root of 900. And again, I'm just going to go back and make sure I answer the question. Find the dimensions of the container. So I know the x value is the cubed root of 900, and my volume was x squared h equals 300. And obviously you're just plugging this back in, the cubed root of 900 squared times h equals 300. Solve for h and you've got your answer there, the dimensions of the container. Well, that's going to do it tonight for us on optimization. So hopefully you've taken great notes, and we'll look forward to some practice tomorrow. Have a great night.